We're still in section 3. Today we're going to look at the graphs of logarithmic functions, and to do so, we need to recall something about inverse functions. So here we have inverse logs in the picture. We're also going to look at transformations. So if you want, pause the video at this time, see if you can determine which equation matches with which graph. The first one would be the parent function, y equals 4 to the x power. Your y-intercept would be 0, 1. Plug in 0 for x, you get out 1 for y. That's exponential growth. The second graph would be exponential decay. That b value is in between 0 and 1, so if I multiply by 1/4, the y values are getting smaller as x gets larger. If I want to reflect over the x-axis, this negative out front would do that. The -5, if that's attached to the x, that's going to move the parent function 5 to the right. If I plug in 5 for x here, I'd get out 4 to the 0 power, which is 1. So 5 should give me out 1. And if I subtract 5, not attached to the x, that's going to move all the y values down 5. So keep these transformations in mind as we move forward. Inverse functions then. What do you remember about inverse functions? Well, one thing should be, if I want to find the inverse equation, I just need to switch x and y and then solve for y. Another thing, if I look at the graph of an inverse function, so let's just take a parabola. The inverse should be the reflection over the line y equals x. So if I take this blue graph and reflect over the line y equals x, I should get the inverse, which is the red graph. And then also if I look at this graph, well, the original graph fails the horizontal line test, which means when I reflect it, the inverse would fail the vertical line test. So if the original graph fails the horizontal line test, then the inverse is not a function because the inverse will fail the vertical line test. Okay, so that's our brainstorm, remembering a little bit about inverse functions. So why do I care about inverse? Well, if I want the inverse of an exponential function, let's start with y equals 10 to the x. To find the inverse, I just switch x and y. So now we're at x equals 10 to the y power, and then I want to solve for y. Well, you might be thinking, well, y is in the exponent, so I don't know how to get y by itself if y is in the exponent. But then you might also be thinking, well, wait a minute. What is a log? A log is an exponent. So actually, the inverse of an exponential function is a logarithmic function. So I can rewrite this as log. Your base is 10. Your exponent is y. And then the argument is x. So these are saying the same thing. This is like saying 10 to the y power equals x. Same thing, but I've just rewritten it, and it looks like that y equals form. Now this is a common log, so I don't have to write the 10 as the base. If you wrote this, these two, recall, mean the same thing. So both of those would be perfectly acceptable for the inverse equation. So the inverse of y equals 10 to the x is just log base 10 of x equals y. So why don't you give these an attempt? Let's see how far you get on your own. Pause the video at this time. So the first thing I do on each of these equations is just switch x and y. And remember, f of x is like the same as saying y. So at this point, this is the inverse equation, but I want to write it in y equals form. So if I want to free up that y, well, the inverse of a logarithmic function is actually an exponential function. So this line is saying the same thing as, well, 10 is my base. The exponent, well, a logarithm is an exponent, so the exponent is x. 10 to the x should equal the argument, which is 5y. And now there's just one move left. If I want to get y by itself, divide by 5. And this is the inverse equation in y equals form. I could write that using the inverse notation. And if I wanted to leave it as 10 to the x over 5, you could, or, feel free to also write it as 1/5 times 10 to the x power. So this is the inverse of the function f of x equals log base 10 of 5x. Second one, switch x and y, so I've done that. You could add 2 to each side. And now I'm kind of stuck at the point of, well, I want to get y by itself, but that's up in the exponent. So now, I can't really get y by itself unless if I convert this to logarithmic form. So I should have y is your exponent. Y equals log, my base is 10, and the argument would be x plus 2. So these right here are saying the same thing. My base is 10, my exponent is y, and that should give me out the argument x plus 2. If you wanted to, perhaps you did not write the 10 in there. So if you wrote something like this, it's implied that the base is 10 because it's a common log. So either of these would be perfectly acceptable for the inverse equation. So the big idea here is logarithmic functions are the inverses of exponential functions. Let's look at an example where we actually graph a log and its inverse. So if I'm starting with a logarithmic function, I would be thinking, well, the inverse should look like an exponential function where I have y equals some base to a power. So first step to find the inverse, switch x and y. Log base 3 of y. So switch x and y, this is the inverse. And then I want to free up that y. I want my inverse to look like y equals something. Well, let's see, my base is 3. The exponent is x. A logarithm is an exponent, so this is my exponent. And 3 to the x equals y. So this is the inverse of y equals log base 3 of x. The inverse is actually an exponential function. If I want to graph these, I could just go ahead and make a table then. So let's pick points to the left and right of the y-axis. So why don't you pause the video, see if you can fill in the y values, and then see if you can fill in some values for y equals log base 3 of x also. Okay, so here are some coordinates on the graph, y equals 3 to the x. If I plug in -2, I'd get out a 9th. -1, 1/3, 0, 1, 1, 3, and 2, 9 should be on the graph of this function. If you remember anything about the inverse functions, if I just switch the x and the y, those should be points on the logarithmic function. So switch x and y, and I get points that should be on the graph y equals log base 3 of x. Whoops, let's see. 3, 1. Okay, and that should be positive. Let's see, did I flip those all correctly? Here's another way, if I don't have this graph to flip x and y, if I want to make a table here, well, this is just 3 to the y equals x. So if you want to make this table without having this original table, you could just do something like this, and I would suggest plugging in values for y. So for instance, what's 3 squared? Well, 3 squared is actually 9. Or 3 to the negative first power is 1/3. So that's kind of an alternate way to generate the same table. I'd plug in values for y and see what comes out for x if I didn't have that first table made. So now if I graph these just by plotting those points from the table, here's your exponential function. And if I reflect that over the line y equals x, or if I switch all the x and y values, I would get the inverse, which is the logarithmic function y equals base 3 of x. And you should be able to see just a couple points here that, yep, those are reflections over the line y equals x. Now let's connect some pieces here of how these graphs are related. First thing to note is that for an exponential function, we had talked about how the base has to be positive, it can't be negative, and it also can't equal 1, because if you raise 1 to any power, you're just going to get out 1. So this 3 is positive, making this base positive. So for logs, that base is never going to be negative, it's not going to be 1. If I start looking at the domain, well, here I can raise 3 to any power. And if I go back to this red graph, it continues on and on forever, left and right. So the domain can be anything. What's going to come out, though? Well, I'm going to have an asymptote. My asymptote would be the line y equals 0. So if I raise 3 to any power, there's no way I'm going to get out negative numbers. Meaning my asymptote is the x-axis, y equals 0. And the range, well, 3 to any power, there's no way I could get out 0, and there's no way 3 raised to any power will be negatives. If you look at the inverse function then, so if I look at this function down here, well, now what's your domain? Well, this only exists to the right of the y-axis. So here it looks like, well, x can only be positive and x can't be 0. So this argument can't be negative and it can never be 0 because 3 to any power can never give me out a negative number, right? This is 3 to the y equals x. So 3 raised to any power can never give me out a negative. It can't give me out 0. So the range of the original should become the domain of the inverse. And the domain of the original should become the range of the inverse. Notice how my inverse function will continue down and upward forever. And if I'm looking at, the y, well, I can raise 3 to any power. So the range, or the y values, can be anything, since that's your exponent. The asymptotes, well, the y-intercept is the asymptote for the original. For the inverse, this inverse graph will actually get very close to the y-axis, but never quite touch it. So asymptote would be the y-axis for this logarithmic function, or the line x equals 0. And then last thing, well, to find the intercepts, my original graph is never going to touch the x-axis, but it will intersect the y-axis. If I want to find the y-intercept, I just plug in 0 for x. So if I input 0 for x, well, 3 to the 0 is 1. And there is no x-intercept. And, well, if I switch these points, if I switch x and y, 1, 0 would actually be the x-intercept for the inverse. And we can go back and see, yep, there it is, 1, 0. If I plug in 0 for y, 3 to the 0 is 1. I get out 1 for x. And then there will be no y-intercept. So these are important features to start connecting between the original graph and its inverse. So now consider the parent function y equals log base 2 of x, which is graphed for you. Pause the video, see if you can fill in the domain, range, intercepts, and asymptotes. So pause the video. Now you should have found that this graph actually has the same domain, range, x-intercepts, and asymptotes as the function y equals log base 3 of x that we just graphed. If you look at this, this is the same as 2 to the y equals x. So certainly I can plug in anything for y. The exponent can be anything. 2 to any power will never give me out a negative number. It'll never give me out 0. So the x values could only be positive. If I do plug in 0 for y, 2 to the 0 is 1. So 1, 0 should be the x-intercept. And there is no y-intercept because the x value can never be 0. So I'm never going to hit the x-axis, but I will get very close, or I'll never hit the y-axis, excuse me, but I will get very close to the y-axis, which means it is an asymptote. The logarithmic function will approach that y-axis, the line x equals 0, but never touch it. So now the transformations that we studied before also apply to logarithmic functions. So, I mean, if I look at my parent function, y equals log base 2 of x, that we had on the previous page. Now, what if I subtract 3, and that's attached to the x, that's attached to the argument of the logarithm? Well, that should actually move the parent function right 3. And if I'm adding 4, that's not attached to the argument, it's not attached to the x, that would move things up 4. Just the same idea behind all the other transformations that we've looked at throughout the book. So if I want to graph the new function, I could take points like 1, 0 and move them 3 to the right. So 1, 2, 3 to the right and 4 up. And that new point should now be at 4, 4. I could take points like 4, 2. So let's see, this was what? 2 to the y equals x. So if y is 2, x would be 4. So 4, 2. And move this 3 to the right, 1, 2, 3, up 4, 1, 2, 3, 4. I would also want to move my asymptotes. So if the asymptote of the parent function was the y-axis, or the line x equals 0, well now that line should be moved 3 to the right. And note that this graph is going by 2's, so 3 would be right about there. So my new asymptote should be the line x equals 3. The domain would move 3 to the right. So if the domain of my parent function was 0 to infinity, the domain of this new transform function would be 3 to infinity. Now note, if I plugged in 3 here, the argument would be 0, and the argument can't be 0, it also can't be negative. So 3 to infinity, not including 3, would be my new domain. The range, I can still get out for anything for y. So this graph continues up and down forever. If I'm now looking at my intercepts, this becomes a little bit trickier. So now let's look at this transform log function. I'm going to go through and solve for x. So I subtracted 4. Now a logarithm is an exponent. So let's see, my base is 2. My logarithm is y, or my exponent is y minus 4, and that should equal x minus 3. So I actually have 2 to the y minus 4 power plus 3 should give me out x. So if I wanted to make a table to graph this function, I could plug in y values and see what comes out for x. If I want to find the x-intercept, that occurs when y is 0. So in my original equation, I could plug in 0 for y and solve. Or I'm going to plug it in here since I've just rewritten it. So now if I make y equals 0, I'd have something like this. That should give me out my x-intercept. So 2 to the negative 4th plus 3 would be my x-intercept. 2 to the negative 4th is the same as 1 over 2 to the 4th, or 1 over 16. So if I plug in 0 for y, so if I plug in 0 for y, my x-intercept is 3 and 1/16. So a little bit tricky here. But same idea as with other functions. If I want to find the x-intercept, just plug in 0 for y and solve. And if I look at my graph, yeah, that seems reasonable that it's crossing the x-axis at a little bit over 3. So let's wrap this up with one last check. Give this example a try on your own, and then I will reveal the answers. So pause the video, and then check your answers. So here's the new graph. Adding 11 attached to the x in the argument would move things 11 to the left. The 2 outside of the argument that's not attached to the log would move things 2 down. And then if I want to find the x-intercept, I just plugged in 0 for y right away. And then if we're going through and solving, careful on this, this is not attached to the argument. It's not part of that logarithm argument. So if I add 2, let's get rid of that first since it's not attached to the argument. And at this point, the base is 5. A logarithm is an exponent. 5 squared should equal x plus 11. So 25 equals x plus 11. And if I solve, I'd get out 14 for x. So if I plug in 0 for y, I get out 14 for x. That would be your x-intercept of this function.